introduce our first speaker, Mr. Michael Bonner. He is the Vice President, Engineering and Technology for St. Clair Systems, based in USA, a lead supplier of the process temperature and viscosity control equipment for industrial fluid dispensing systems. He is an electrical engineer. Over the years, he has spent in a wide variety of industries, including audio systems, medical equipment, HVAC, and also appliance controls, metal stamping, and even the manufacture of gasoline pumps. For the last 25 plus years, he has focused on the science of point of application temperature and viscosity control in fluid dispensing processes. So let's welcome Mr. Michael Bonner to give a presentation on the controlling the rubber bonding process, reducing the solvent usage, and improving outcomes.
Excellent. Well, hey, thank you for allowing me to be here today, and welcome everyone. Let's get right down to business. We all understand the importance of automation as a means of improving application process control. This usually brings to mind images of robotics spraying parts with very high precision. But there are other forms of automation that complement both manual and automated applications that improve process outcomes and thereby increase predictability and repeatability. So today in this presentation, we're going to talk about these less evident tools and how they can be utilized with bonding agents to improve the overall performance. As Param mentioned, you may not be familiar with St. Clair Systems, but we design and manufacture advanced point-of-use temperature and viscosity control systems for industrial fluid dispensing processes. We've been doing this since 1990. Over that 30 plus years, we've amassed more than 3,500 active installations all over the globe. I often joke that we have applications on every continent except Antarctica. But we specialize in both recirculating and dead-end systems, and we handle everything from low viscosity materials like water and solvents that are down around 1 centipoise, all the way up to high viscosity sealers and adhesives that are in excess of 1,000,000 centipoise. To handle these applications, we have equipment that can work all the way up to in excess of 400 bar. So who cares? And the answer is lots of folks across myriad industries, as you can see here. Each one of these demanding manufacturers uses fluids in their process, and they're critical to the outcome of their product assembly. Each one of them has had specific issues with those processes and come to us for solutions. Each successful project with customers like these increases our understanding of the ramifications of temperature and viscosity across a vast array of fluid dispensing applications. Now, this is a shameless advertisement for St. Clair Systems, but because many of these are critical coding applications, it's also the reason that we're qualified to be here today discussing this topic. We build all different kinds of systems. We build systems that consume a large room, okay? In this instance, these will be over 10 meters long and weigh more than 3,000 kilograms and cost upwards of $500,000. And those are the big systems, but we also build smaller systems as well. This is a thermoelectric unit. It can sit on a tabletop. It is basically 40 centimeters square, and it weighs less than 15 kilograms and costs less than $5,000. So it's a vast variety of different systems for virtually every application, regardless of size. And then we have a line of viscometers, and that includes our VTS inline unit, which is shown here. It's designed for continuous in-process control. It has no moving parts. It's constructed entirely of 316 stainless steel, so it's compatible with every process fluid out there. It's just 21 centimeters long and 6 centimeters in diameter, so it's small enough to fit easily into virtually any dispensing system. And this allows you to eliminate the uncertainty of manual viscosity measurements and manual adjustments for less than $5,000. And of course, we're proud to announce that we've successfully incorporated St. Clair Systems India Private Limited with our home office and assembly plant in Kolhapur. As Ravi often says, this gives us the ability and our customers in India the opportunity to obtain Western technology and quality manufactured in India at Indian prices. So you can check out the website there, www.stclairsystems.in, and you can get more details there. So let's jump into the topic for today, enough of the introductions. We're going to start by talking about the temperature-viscosity relationship. This is the fundamentals behind what's going on. And these are the things that create issues in dispensing systems in the first place. We're often asked why we focus on temperature. And the answer is that temperature affects viscosity. And viscosity affects flow, pressure drop, volume of the dispense, and the ratio in the case 2K materials. But most of all, the spray pattern. As we can see here, we can see how the spray pattern changes with a width increasing proportional to the temperature. But this phenomenon, even though it's related to temperature, it's actually caused by the change in viscosity. So that begs the question, what is viscosity anyway? And it's a really good place to start our discussion. I like this explanation because it's simple. The property of resistance to flow in a fluid or semi-fluid. Now, we all understand that water is a consummate definition of a fluid. But what's a semi-fluid? And because you're all in the industry, you probably have a lot of things popping into your head that are specific to your particular process. But I'm going to pick something a little more general, something that you maybe didn't think of. Honey. Think of honey if you place it in the refrigerator. It gets thick, really thick, almost solid. But if you take that honey out of the refrigerator and you place it out in the hot sun, it starts to warm. And as it warms, it thins out significantly, and soon you can pour it, almost like water. Now, the change in how it flows represents its change in viscosity. And in this case, like we'll discuss all day long today, the cause of the change in viscosity is the change in temperature. For instance, here we see the viscosity versus temperature curve for Parker-Lord's Chemlock 220, which is a common solvent-borne bonding agent. And this was measured in St. Clair Systems India's lab. It's the typical curve we're all familiar with, okay? The viscosity is falling as the temperature increases, and though it looks like a linear relationship with a slope of about 0.9 seconds per degree C, if we apply a linear trend line, it reveals that, just like with most modern coatings, this is actually an exponential curve. Now, another interesting fact is that Parker-Lord's DS3105 datasheet recommends that this coating be applied at a viscosity of 22 to 28 seconds, which, if you look at the scale, on the left here, you can see that it's below the minimum value in this data set, which means that this compound must be diluted if it's going to be sprayed. Now, this same data sheet recommends that this coating be diluted with 25 to 50% xylene. And from this graph, we can see the viscosity versus temperature curves for various dilutions of Chemlock 220. Again, these were prepared by St. Clair Systems India in their lab and measured there. Now, if we project the recommended spray viscosity range of 22 to 28 seconds across these curves, we can see the importance of the interaction between dilution and temperature in the actual viscosity of the fluid. It's apparent that depending on the temperature, dilutions as low as 5% can actually be used, whereas dilutions of 25 to 30%, which is on the low end of the recommended range, can produce viscosities that are actually outside of the recommended range. It also seems pretty clear that dilutions greater than 30% will produce viscosities that are below that recommended 22-second minimum for spraying across nearly all temperature conditions. So this is a really important finer point about the compound and its usage. But what many people don't think about is that adding solvent alters that carefully developed coating formulation that Parker Lord worked so hard to create. And the solvent creates many issues within the application process. Now, first, it represents excess cost because every drop of added solvent has to be driven off in the oven during the curing process. And in addition to the environmental concerns, it also represents a risk to our operators. Now, to make matters worse, too little or too much solvent can cause defects. And we can plot these defects on a continuum as we see here. Now, if we have too little solvent, we get dry spray and all of the associated issues with adhesion and all of the other issues that you're used to, uneven coatings, etc. If we add a little more solvent, we reach the optimal point at which we should be using the product to get the optimal performance level. But if we continue to add solvent, we begin to get issues with cure, which, as we add more and more solvent, can progress into problems with adhesion and blistering. And as we add more solvent, even solvent pop. This is why the temperature factor is so important. It's important to understand the impact of viscosity in our process. Proper coating viscosity is key to successful product outcomes. Yet, even in today's modern applications, we usually make one viscosity adjustment, and it comes at the beginning of the process. And we usually make that adjustment by adding solvent. And we generally ignore the impact of temperature on our process outcomes. Now, there are a lot of factors in our environment and in our process that affect temperature. And things like ambient temperature, which is the first thing you think about. What's the ambient in the room? But there's also the coating storage temperature. What temperature did you store it at? Did you store it outside in the hot sun? Did you store it inside where it's cooler? What's the volume of the source container? That's important because it's a thermal mass, and it takes a long time for a thermal mass to change temperature. And then there's the rate at which the coating flows in our process. And if we're recirculating it, it's the rate of recirculation. And what's the path of the recirculation? Does it go up through the truss level and down to our dispensing station? Or does it flow maybe under the floor in a basement area where it's cooler? The path and the recirculation rate and the dispense pressure also all add together to determine the type of pump that we use and the energy that pump puts in the form of horsepower. While we know that the pump adds heat because it's adding energy to create motion, it's doing that in opposition of shear, and there's shear in all of our systems. There's the pump, the agitators, there's regulators, there's nozzles and fittings, and all of these add shear to our fluid. Shear equals friction, and friction equals heat. Therefore, shear equals heat. So all of these factors play into changing temperature in our process. And of course, we never want to forget the substrate temperature because it's also important to the overall application process. So how do all of these temperature influences affect the film formation? If we're going to discuss film, we need to start with the perfect film. If the viscosity can be controlled and the system set up such that atomization and deposition and film build are even across the part, the cure will also be even and the result significantly more predictable. This more consistent surface will also produce a better bond. Not only will the bond be stronger, but the layer will also be significantly stronger as well. But creating the perfect film requires perfect conditions. And more often than not, conditions are not perfect. As we've already seen, if the fluid temperature is wrong, it will affect atomization, spray pattern, flow out, etc. The result is an uneven film across the surface of the part, as we've demonstrated here. This can have a significant impact on our film cure. As we can see, the thinner film areas are going to cure more rapidly than the thicker film areas, and that makes perfect sense. The uneven surface will also have a negative impact on our bond performance. It's also possible to create blisters from solvent entrapment under the cured surface of the coating. As it cures, the solvent gets trapped and blisters form as that solvent tries to evaporate up through that sealed surface. And this has a negative impact on bond performance in the Chemlock layer itself. Now, to make matters worse, if these thinner film areas that we're looking at are within coating spec, the thicker film areas represent excess coating. And when we apply excess coating, we're adding to our costs. So that's really important. Now, these things all add up to create defects, okay? And what defects do we attribute with these temperature-induced changes in the Chemlock and primer viscosity? And they're all the same ones that you're used to. First, there's the interlayer failures. These are the result of poor bonding between the substrate and the primer and the Chemlock and the rubber itself. So there's 3 different transitions there where these failures can occur. Then there are the intra-layer failures. These are often called cohesion failures. And these are the failures that happen within the layers themselves. These are all caused by temperature-based viscosity variations that manifest themselves as variations in film. So we have to establish our desired dry film thickness range. Okay. Now, on the data sheet provided by Parker Lord, the primer should be applied at 5 to 10 microns as a dry film thickness. Now, the top coat should be applied in the 18 to 25 micron range for a total dry film of 25 to 30 microns. Likewise, if you're doing a single coat, it too should be applied in the 25 to 30 micron range. These are the optimal film builds to get good bonding and optimal film strength. So let's return to our film build example here, and we can see that we have a film thickness range between 25 and 30 microns, okay? And the areas below that 25 microns, as shown here, will have insufficient film. And it's hard for our rubber to actually get down into those cracks and crevices. So it creates a bonding issue, okay? This is our interlayer bond issue. Conversely, the areas where we're looking at too much film being applied, okay, this is above the 30 micron range. And this compromises the strength of the layer itself. This is where we get our intralayer failures, where the failure actually occurs within the ChemLock layer itself, not at the bond line. So our goal must be to stabilize and optimize the viscosity of the coating material at the point of use, which in spraying systems is the nozzle orifice. Now, in order to get a predictable film repeatedly, no other material temperature in the system matters as much to the outcome of the coating process. So how do we manage that? And here's an example of our bonding agent temperature control system installed on an automated spray system. It's an ideal solution because it is low in cost, it's small in size, and it has both heating and cooling capability, which is important because it allows us to maintain consistent temperature regardless of changes in the ambient from morning to night and season to season. It's got a low power consumption, which makes it economical to operate on a production basis, and it utilizes our recoilable coax hose technology to carry the temperature control all the way to the gun to establish point of application control. And that's very important to maintaining consistency through our manufacturing process from day to day, morning to night, season to season, and importantly, from batch to batch. And it also works well for manual applications too. So if you're spraying by hand, this can help as well by making sure that you always get the proper atomization and fan pattern, and that eases the stress on your operators. So when is temperature and viscosity control necessary? Well, When you're dispensing a viscous material that's sensitive to temperature changes, when manual, automated, or robotic equipment is being used, when repeatable results are not just desired, but required, when quality requirements are high, and so in short, always. What we stress is that you take your bonding layer from this to this, and the benefits are obvious. You get improved quality. You get increased first pass yield, reduced bonding agent usage, reduced primer usage, reduced solvent usage. So that adds up to cost savings. But that's extended because you also get reduced rework costs and reduced scrap costs. And best of all, for your relationship with your customer, reduced warranty costs. And then to help our planet, you get reduced environmental impact. And to benefit your operators and their families, you get reduced operator exposure. And so with that, I'm going to wrap up this section of the program and turn this back over to Param and allow us to move on.
Thank you, Mike. That's a very good informative presentation on the rubber bonding, controlling the rubber bonding process, reducing the solvent usage, and improving outcomes by Mr. Michael Bonner.